we'll start a new recording that isn't so me getting organized. Morning, morning one. All right. Okay. Man. All right. Growing pains, growing pains. Yeah. Technical difficulties add authenticity. Yeah, that's true. Struggle City here. And I just taught a class. I don't know, but I think everything, all the batteries are like running out. Anyways, let's get started. There's not nearly everyone here, so well, maybe they'll trickle in, maybe not. Okay. So if we go to Moodle, then I posted this fundamentals part 1 sheet that we'll work through. So what I'm going to do is I'm just going to pull little parts from it. So I'm going to put this in, open it in Notability. And so later on, so if you're into printing stuff, I would maybe print the one that we have at the end of the day instead of this one, because I'm going to be adding notes to it. But however you want to do things works. Okay. So I'm going to rename this Math 120. All of a sudden, typing's getting caught up. Is it the 50th today? Yeah. Okay. And then I'll post these notes afterwards. Okay. Or maybe what I should do is also have a side gig here. Guess what I'll do, is I'll do fundamentals part 1. Okay. And so what I want to do is in these first 1 or probably 2 weeks is just really iron out all the fundamental things that you should be bringing into this course. So it can get kind of boring if you are feeling really comfortable with math and the math that you're bringing into the course. But if you're feeling a little bit scared maybe of taking math, then this one's for you. So we're just going to work through kind of the basics of the math that I expect you to have, okay? And so it can be a little bit slow if you're feeling comfortable, but I'd rather that than go too fast through it and then have to revisit it later again. Okay. So what I'm going to be doing is I'm going to pull little sections from this handout, and we'll just talk about it as we go. So section 1.1 is about real numbers, and real numbers are just any number that you can think of from negative infinity to positive infinity, all those numbers in between, those are all real numbers. There are imaginary numbers, but we're not obviously going to get to those in this course. So the real numbers, if you imagine a number line, nose is all runny, it wasn't earlier. if you imagine a number line from negative infinity to positive infinity, which is really hard to imagine, but then you have the set of real numbers. Okay, so all our numbers that we can think of, and we just use little arrows each way to show that it keeps going and going and going. Infinity is not a number, it's an idea, a concept. So it just keeps going and going and going and going, and somewhere down here in the center we've got 0. Okay. So the set of real numbers is denoted by this kind of fancy capital R. So it's got this double back, and it's a capital R. So this fancy R is the set of real numbers. And we'll talk more about sets in a little bit here, after we review just kind of some basic math stuff. Okay. So the set of real numbers is the most common set of numbers that we talk about. Sometimes we want to narrow it down. There's the set of natural numbers, which is also on the handout. These are your counting numbers. Oh, hello?
Sorry, I missed that. Could you say it again, please?
Siri's listening. I don't know why. I don't know what I said, but the set of natural numbers, the counting numbers, the set of natural / counting numbers. So the natural numbers or the counting numbers, 1, 2, 3, 4. So it's whole numbers. You can include 0 if you want to. There's some debate. Is it part of the natural number set? If you want to, you can. If you don't want to, you don't have to. Right? But if you think of the natural numbers as, yeah, probably heard the, I'm not even going to say it, in series. Decided to put in maths tutor. She's always listening. That's okay. She's there when I need her. So the set of natural numbers we're not going to use that much, but very useful is a capital Z with a fancy back on it. This is the set of integers, right? So whole numbers from negative infinity to positive infinity. And so the set of integers come to play quite a bit, right? And so this is the set of integers. Right? And so, and these are whole numbers from negative infinity to positive infinity, right? So think things like -3, -2, -1, 0, 1, 2, 3, and so on and so forth. So the set of real numbers and the set of integers are the ones to have a handle on, right? So I'll put a little star there. Definitely remember these. Because I will use them just when I'm talking. So remember these. And know what I mean when I say the set of integers. We can also talk about rational numbers, which also leads us to irrational numbers. Rational numbers are just any fraction that we can represent with just an integer over an integer. Okay, so rational numbers are things like, and we're going to do this a lot, right? We're going to use variables in place of numbers. So we use letters quite a bit in place of numbers. And so here, we'll start here and then it doesn't stop for the whole course. It never will. So we'll just have to get used to it. So rational numbers have the form m over n. Now the printer's going. Too much. Where n is not equal to 0, right? And m and n are integers. Oops, integers. Okay. So here's an important rule, right? Just as a refresher, right? We cannot divide by 0. You can try to do it on your calculator. It'll just tell you there's an error. In math, we cannot divide by 0, right? So just put that in the old noggin, right? We can never divide by 0, right? And so we say that, okay, well, n can't be 0. Well, that's just because, well, we can't divide by 0, right? So often we'll just have to say all these things that should be pretty obvious, right? But we have to explicitly say that n can't be 0. So now that we're talking about fractions, let's do a little brush up on our terminology, right? And so a fraction, so a rational number is a fraction. I think most people are more comfortable calling them fractions. And a fraction, right, has a numerator over a denominator. Okay? So it has a numerator over a denominator. So because I'm going to use these when we're talking, right? So then we have to be able to keep track of, okay, which one's the numerator, which one's the denominator, whether that's a matter of just memorizing it, or I always use the numerator is numero uno, so he's on top. And then of course the other one is on bottom. For a lot of these things, you only need to remember one of them and then the other one follows. But yeah, the numerator is on top, numero uno, number one. So he's on top. And then the denominator is on the bottom. Okay? But we will use these when we're talking, so we need to remember those. These little terms. Okay. So a rational number is just any number that we can express as an integer over an integer. So there can be things like if we try, I'll just pick one from the list here, 157 over 495 on your calculator, right? If you try to do it on your calculator, 157 over 495, oh, I should say, depending on what calculator you have, if you're using your phone, I think it defaults to just the decimals. Some of these calculators show the exact answer, which is actually really nice, really luxurious, because it'll show the simplified exact answer. And the reason it does that is because if we go to decimals, so in case anyone has a calculator kind of like this that shows the exact answer, you can change it using the S arrow D button. Okay. Or there's also the approximately equals, but then you have to go shift equals to get the approximation. So it is equal to 0.31717171717, and I'll do the dot 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 because that's what it's equal to. Okay. Or, right, because the 17171717, this is all just repeating. So what we do is, you might remember that you can write 0.317 with a bar over the 17, and that'll show the repeating. Okay. So here things are still equal to each other, right? So this is actually equal to 157 over 495. Where we need to be careful is if I start to write something like, well, I'm going to start with the error, right? Equals 0.317. That's not true, right? Oh yeah, so Tushar asked if we can write it as 0.318. No, so that's what I'm getting to here, is we could write 0.317, right? But that's not exactly true. So what we do is you have to write approximately equal to, right? And so that's just a squiggly equal sign is approximately equal to. So we have to be really careful about, I'll clean this one up. About using our equal sign, because sometimes you don't mean equals, you mean approximately equal to, and then you're safe to go, right? But we have to keep in mind that sometimes we're using approximations. In fact, whenever we use decimals, we're using approximations. Especially for rounding decimals. So, so then we would have to be really careful about using the approximately equal to. So it is approximately equal to 0.317. There's usually no harm in cutting it that short, but we have to make sure that we say it's approximately equal to. Okay. So in this case, right, even though we have this repeating structure, we can still express it as an integer over an integer, right? 157 over 495. So when we get into irrational numbers, which we'll do now, so irrational numbers cannot be expressed as a ratio of integers. Okay. So there are some common irrational numbers, right, that just continue. There's no repetition, or at least not long enough for us to capture. So a common example would be pi. Pi is an irrational number. Pi is approximately equal to 3.14159265, stealing it from that handout. Okay, it's not equal to that because it keeps going and going and going, but in terms of our calculations, maybe this is good enough, right? In fact, your calculator has a pi button, but even your pi button on your calculator, it's using an approximation. So even things like root 2, if you take the square root of 2 on your calculator, it just keeps going and going and going. And your calculator doesn't indicate that, right? And so we'll use all our decimals, but just understand that it would keep going and going. 1.414213562. Okay. Approximately. We'll even see E later on, but these are just some irrational numbers. Okay. And we use the approximations, but ideally we use the exact numbers. Okay, so here, these are the exact values. And as soon as we get into decimals, right, these are our approximations. Approximations. Okay. So we have to keep track of the exact value and the approximation. Even up here, when we did 157 over 495, this here is the exact value, and this is the approximation. Okay. Okay. So, kind of been catching the questions as they come in here, so that's good. Let me grab the next piece that we're going to talk about. So some properties of real numbers. Now, a lot of these are pretty basic, right? But that's what we're doing here. We're just brushing up on things that we should know, right? Converting the fraction to a reduced form would still be rational. That is correct. Yeah. So as long as you're able to express it as an integer over an integer, it's still considered rational. Yeah. Cool. Cool, cool. Okay. So here we go. The commutative properties and the associative properties should be very familiar, right? And so probably not by name, right? So you probably don't say, oh, I'm going to use the commutative property, but we know what it is. And so what it says is that if you have A plus B, that is the same thing as writing B plus A. Same thing with multiplication. A times B is the same thing as B times A. Right, and so we can rewrite these as long as we're only adding or only multiplying, then the commutative property says that the order doesn't matter. Right? Subtracting is different, right? Even division is different, but for adding and multiplying, the commutative properties are pretty basic. For the associative properties, remember, we have to keep track of bed mass. So if we have brackets, exponents, division, multiplication, addition, subtraction, right? We have to do those in order. And so if we have brackets, we have to be careful. But if we scan the line here and we see that we're only adding, then the brackets can get moved around, right? Same thing with multiplying. So for adding and multiplying, the brackets don't really matter. We can add and multiply in any order that we want. The kind of tricky one, not terribly tricky, but kind of the only one on here that's really worth mentioning is the distributive property, right? So if you have A times B plus C, then you can pull that A inside the brackets and then dissolve the brackets. So here, if you have A times B plus C, what happens is that this A goes on the B, multiplies the B, and and then it goes on the C, so it multiplies the C. So what that looks like is you have A, and if you want to, you can keep the brackets, you don't have to. A times B plus A times C, which is just going to be AB plus AC. Just as a note, what you'll see is that I often don't use a multiplier. So multipliers, you can have A times B. I don't like that one because when we start involving x's, it makes it really hard to read. And so you can have A xb or A dot B. But my dot, if I get sloppy, start looking like minus signs. So I just don't have a multiplier, and I just write AB, and then it's implied that they're multiplying. And so those are the multipliers that we can use, but you'll want to be careful. Be careful that it doesn't look like an x, right? Because we'll use x as our default variable later on. So that's why it's so important to kind of stop using the x as the multiplier and either use the dot or nothing at all. Okay, same thing with the next option in the distributive property. The only thing that changed is having the A on the right-hand side instead of the left-hand side. But as long as you think of B plus C as one thing, right? You can have it as one thing times A, then that one thing times A or A times that one thing, it doesn't matter. So you can switch the order around and then it'll behave the exact same way. Okay. So here, let's do a little example. If we have, and now I am going to involve x's, so that's why we have to be so careful. 5x plus 1 times 3. Well, like I said, as long as the 5x plus 1 is we think of that as one thing, right? Then I could write 3 times 5x plus 1 or 5x plus 1 times 3. It doesn't matter. The order doesn't matter. I'm going to scoot this over here. Give myself a little bit more room. So what I have, if I keep the brackets around the 5x, and of course, as we get going in the course, right, you can skip some steps here, but I'm going to show every little step. So 5x times 3 plus 1 times 3. Sometimes I'll use the brackets around the 3. Notice how, there. How about that? I should add it to my list of multipliers. A times B in brackets. Kind of off to the side here. So we've got lots of options for multipliers. 5x times 3, well, the 5 and the 3 multiply and then they multiply x. And so we've got 15x plus 1 times 3 puts me at 3. So there I've used the distributive property to eliminate the brackets. Okay. So if we want to talk about negatives, right? Negatives are this this kind of different beast. They are undercover subtraction, right? And so adding and subtracting, well, subtracting is just adding a negative, right? And so once we get kind of on board with that, then it'll make more sense why we focus on rules for addition. Well, because they apply, but now we need to keep track of the properties of negatives, right? How negatives behave. Sorry. So a negative number is just, so if you have negative a, well, all that is -1 times a, right? So you can pull that -1 outside or distribute it onto the a to get a negative value, right? And then, so I think we're all kind of on board with, okay, if you take the negative of a negative number, you get the positive value, right? And if you have one negative and one positive being multiplied, regardless of the order, you get a negative number, right? And so here, property 2, negative of a negative gives a positive, whereas multiplying a negative and a positive make a negative. Multiplying a negative and a positive give a negative. And the fourth one, multiplying two negatives gives us a positive, right? So a negative times a negative gives a positive. Negative times negative gives positive. Okay, so we'll want to keep those in mind. Property 5 and 6, well, that's just the distributive property, right? And so if I kind of do a different color down here, 5, if you have negative a plus b, if you think of that negative as -1, right, then essentially you've got -1 times a, right, just bringing it in, distributing it across the brackets, -1 times a plus -1 times b. Right? I like to just keep the plus in here. I like to just keep out here. If it's negative, right, I like to keep it that way and not skip too many steps until I'm very comfortable with what I'm doing. -1 times a makes -a, and then plus -b is technically plus -b, right? But plus -b is subtracting, right? So -a minus b. So that's where subtraction comes from, right? So here, this is technically what subtraction looks like. Technically. Okay. So -a minus b, and then same thing if you have, what was the last one? I guess I should keep with the same color. -a minus b. I'll go a little bit faster this time, right? Because it's the same thing, just with a minus. So now I get negative A, keeping that sign there, minus negative B. Right? The negative of negative B makes positive B, so this becomes negative A plus B. And then all they've done in that little excerpt there is they've just moved the positive value around. So this is the same as B minus A. We're allowed to do that. Negative A plus B is the same as B plus negative A, right? But then it just becomes minus A. Okay. How about we do a little example? Right, without parentheses. Parentheses. The first one we'll do is just quick 3 times x plus y, right? Dealing with variables, but getting more comfortable with variables is going to be really important. So here, I'm just going to distribute the 3 onto the x and the 3 onto the y. So there's nothing really going on here, but this just becomes 3x plus 3y. Not much else to it. But what if I threw a little curveball here? What if I got you to do 3a and then bracket times b plus c minus 2d? And I wanted you to write this without parentheses, meaning expand this thing until there's no parentheses. So I'm just gonna pause the recording and let you work on it for just a little bit here. All right, so we got an answer in, so that tells me I had enough time to work on it. So we've got 3a being distributed. So as long as we keep our wits about us, right, and treat 3a as one thing, right, then 3a is gonna go on b, and then on c, and then on 2d. So this becomes 3a, and to emphasize, and you don't have to, but to emphasize, I'm going to put brackets around the 3a, and then around the b, plus 3a times c, and then minus 3a times 2d. You could have done plus 3a times negative 2d if you wanted to, just as long as you pick a lane and don't do both. So now I get 3ab, right? If I ditch those brackets, they're not doing anything for that one. Plus 3ac, same deal. And then I get minus 3a times 2d, puts me at 3 times 2, which is 6ad. You're correct. Good. Okay. Nice work. So, nice. All good. Let's talk about fractions. So, properties of fractions, just a little reminder because it might have been a while since you worked with fractions, right? But fractions have all these rules. If I say you have to have a common denominator, that probably sets off some alarm bells, right? Oh, there was something about common denominators. Right, and so we'll talk about that. But we'll work through the rules for dealing with fractions. We're going to deal with a lot of fractions in this course, and so I need you to be fluent in these rules. And it's going to take some practice, but we're going to get there. Okay? I'll show you the tricks of the trade. All right. So all the rules are on here, but they're kind of hard to read, I guess, but they're there and they're summarized. So, but I'll just write them all out. Multiplying fractions. We start with multiplying. Usually we start with adding, but in the case of fractions, multiplying is actually the easiest thing that you can do. So I will be using variables to show all these rules still, right? And then I've got a kind of a big couple of examples that we can go through later. So multiplying fractions. So a fraction, remember, is something like a over b times c over d. Okay. Just as long as b can't be 0 and d can't be 0, right? We can't divide by 0. And so I'll make a little note here. B not equal to 0 and d not equal to 0. But those are just math rules, right? But we do have to say them whenever we can and state our assumptions. So if we're multiplying fractions, if we multiply, we just multiply across the top and multiply across the bottom. So we multiply the numerators and we multiply the denominators, and we just get to AC over BD. So we just multiply across, and then we just get them smushed together, right? So that's why multiplying fractions is the easiest thing we can do with fractions. I'd say the second easiest thing we can do with fractions is actually dividing them, right? And so dividing fractions, again, I'm going to assume b is not 0 and d is not 0, but I'm not going to say it because I set it up above. But I've got a over b, but now I'm dividing two fractions, so I've got a fraction over a fraction, right? So I've essentially got four things stacked on top of each other. And to indicate that I've got one fraction and then divided by another fraction, I'm going to use a longer line. I've over-exaggerated it here, but it is really helpful to keep track of, okay, well, this fraction's over this fraction, so I have a longer line there. So I've got a over b over c over d. So what happens is, and I don't know, your high school teacher probably had some sort of thing, but in my undergrad, my teacher is always saying, flip and kiss, flip and kiss. Flip and multiply, I think is, I don't know, it works too. But flip and kiss or flip and multiply, what other things have I heard? They're not coming to mind, but there's some other ways that we can remember it. But what we're gonna do is this fraction in the denominator flips and multiplies, okay? And so whenever I have to divide fractions, I always do this, right? I take my fingers and then I just hold the top one steady, and then I flip and multiply, right? And so this has to flip and multiply. Okay. So what it ends up looking like is that we've got, and I should scoot this down here. We've got A over B is just holding steady, but what happens when I flip and multiply is that now all these fractions are on the same level, or at least in my mind, I think of them as levels. So now I can just write A over B times, and then C over D gets flipped and multiplied, so I get D over C. But now what's really nice is that now I'm just multiplying fractions, right? So now I can just multiply across. And so what I've got here is AD over BC, right? Once I flip, right, I have to make sure that C is not 0. So C can't be equal to 0. As soon as you're dividing by 0, you're hooped. So all these things won't really come into play, but I do have to say it. So dividing fractions, it might feel like a lot of work, but it's not really. In fact, sometimes it'll be easier if we can make fractions so that we're dividing fractions, mostly so that we can cancel things, right? And so sometimes, oops. Sometimes our math will be made easier if we make fractions, right? So sometimes, I'll underline that because that's not always true, but sometimes our math will be made easier if we make, so I'll put quotes around the make, if we make fractions. Okay. For example, right, we know that 2 is the same as 2 divided by 1. Okay. So what if we had something like, and this is just off the cuff here, but as a quick example, right, what if I've got 3x over 4 divided by 2? Okay. That's going to be made easier if I just make, so if I make it be a fraction over a fraction, then I can just do over, so 3x over 4 over 2 over 1, because now it's easier for me to visualize this flip and multiply. So then this becomes 3x over 4 times 1 over 2, right? And now I'm just multiplying across, so then I get 3x over 8. Right? So sometimes things will be made easier if we just make fractions, right? So that's just a little heads up and a cool little trick that we'll use later on. I just wanted to highlight it here because it does come up. Okay, on to adding fractions. Not as fun. It's fine if you have a common denominator, right? But so adding, I'll put and subtracting because it requires the same thing. So and subtracting. fractions. We need to have a common denominator, right? Meaning the denominator in each of the terms has to be the same. So we need to have a common denominator. If we do, then that's great. So if we have A over B plus C over B, right, here, we've got that common denominator, oh, right underneath. Common denominator. Okay. So what happens if we have a common denominator, then we can just add the numerators and use that common denominator. So it's a little bit different than the multiplying because the common denominator just becomes the denominator. So we've got A plus C over B, which is that common denominator. So a little bit different, right? And a lot of the time, we're not going to have that common denominator, right? And so what we've got, right, if we need to make a common denominator, there's a couple of different things that we can do. My way is definitely not the fanciest way. It's not even really the cleanest way, but I would say it's the easiest way to get a common denominator. Okay? So often we will need to I'll do make in quotes again, because we're just kind of forcing things, we're manipulating things using math to make them easier to deal with. So often we'll need to make a common denominator. Okay. There are many ways to do that, okay? Many fancy ways. And if you're comfortable using those ways, then go ahead, do it. We'll get to the same answer eventually. But I will say that there are many ways to find common denominators. But I will only show you the way that I find is the most foolproof. But I will show you the most foolproof way, because that's the way I use. Oops. Okay. So what my method, it's not my method, the method I use relies on the fact that we can multiply any value by 1 and still have that number unchanged, right? So here, the trick is that we can multiply any number. We can multiply any number. Oops. By 1, and it will be unchanged. And it will be unchanged. Okay. For example, right? We've got 3 times 1, well, that's just 3, right? 1 times A is just A, right? So I can multiply things by 1. Hopefully you'll also agree that 4 divided by 4 is 1. 8 divided by 8 is also 1. B divided by B is 1, right? So I can take any number and turn it into a fraction as long. So if I'm going for 1, right, I just take the number over itself. And then I have a fraction that I can deal with, and I can multiply by 1, right? But not really 1, just a convenient 1. Okay? So to get common denominators, what I do is I pick convenient values of 1. To get common denominators, I pick convenient values of 1. Right? So in general, right, if I've got A over B plus C over D, right, the easiest common denominator that I can find between B and D is just B times D, right? They're both going to be in there. They're both going to be factors of it because I forced it to. So that's what I mean by kind of the most foolproof is here I'm going to use B times D as my common denominator. Use BD as my common denominator. Huh? So that's the trick that I'm going to use. So regardless of what's going on, I'm going to take my 2 denominators and I'm going to multiply them together, and that's going to be my common denominator. So when I look at this here, that means I've got A over B, and then to get B times D in the denominator, I need to multiply by D. So what I do is on this term, I glance over here and I make that my convenient 1, right? And so what that looks like is I do times D over D, that's just times 1, right? D over D is 1, so I'm multiplying by 1, fair game. And then I do the same thing plus C over D, right? Now I'm over here on this term, and I still need to get B times D or D times B. Order doesn't matter, right, if we're multiplying over here. So what I'm looking at is from this term, I glance over here and I say, oh, okay, I need B over B here. So times B over B. Right. Notice that here, now we're just multiplying fractions, which is the easiest thing that we can do with fractions, right? And so what we get is we get AD over BD plus CB over DB, but because I want to show that they're a common denominator, I'm just going to switch the order quickly here. So I'm going to have over BD. Okay. So now I've got this common denominator, right? So now I can just add these things up. So I get AD plus CB all over that common denominator, BD. A lot more work, but once you get the hang of multiplying by 1, right, picking a convenient value of 1, then it's actually pretty fun, and it just kind of flows. All right, how about we do some examples of this now? So an example, let's try 3 over 10 plus 4 over 15. Okay. Give you just a quick little minute to work on it. Noticing that there is no common denominator, so you will have to make one, right? And that's exactly what we did here. So my common denominator, I'm gonna make it just 10 times 15. So like I said, of course, there are nicer ways that we can do, right? But this is the easiest way and works every time. So what we're gonna have is we're gonna have 3 over 10, and then just to show that the trick that I'm using, I'll use a different color, because from 3 over 10, I've got an answer in already, so that's good. 3 over 10, well, to get 10 times 15 in my denominator, I have to multiply by 15 over 15. So times 15 over 15, and then plus 4 over 15, but to get that common denominator, I glance over at the denominator of the first term, and I see that it's 10, so times 10 over 10. So now, 3 times 15 is 45, over 10 times 15 is 150, plus 4 times 10 is 40, and then 15 times 10 is 150 again, right? So now I've got that common denominator that I wanted. And so now, right, now I'm allowed to combine the two. So now I get 45 plus 40 all over 150, putting me at 85 over 150. Now 85 over 150 might simplify. If I were you, I would probably just leave it there, right? You can check with your calculator, but I would probably just leave it there as 85 over 150. So 85 over 150, you could simplify as 17 over 30, but I would just leave it as 85 over 150. Let's do one that's a little bit harder. You ready? What if you have 2 over 5 plus 1 over 2? So far so good, right? But dun, 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 divided by 1 over 10 plus 3 over 15. So I'm going to pause the recording here, start recording again. I did forget, but here we go. So just showing where those little multiply by 1s are going. I've used light blue again. So I've got 1 over 10 times, and in the denominator of the second term, I've got 15. So 15 over 15 plus 3 over 15 times 10 over 10. So now I'm multiplying 4 sets of fractions, right? So I can do those individually. In fact, this whole time, I'm going to be just working on the numerator, working on the denominator until it's simple enough for me to have a fraction over a fraction, right? So that's what I'm working towards because there's no other way to start it. So we've got 2 times 2 is 4 over 5 times 2 is 10, plus 1 times 5 is 5 over 2 times 5 is 10. Common denominator, phew, right? 1 times 15 is 15 over 150, right? 10 times 15. Plus 3 times 10 is 30 over 150. Again, I've got that common denominator that I need. And so now I can add these fractions safely because I've got common denominators. So I've got 4 plus 5 is 9 over 10 divided by 15 plus 30 is 45 over 150. Right. Now I've got a fraction over a fraction. So now I know how to divide that. I'm going to flip and multiply. Right, and so I've got 9 over 10 times 150 over 45. Just make a quick little note here that this has to flip and multiply, and that's what's going on down here. So if I do 9 times 150, I get 1350. And then 10 times 45 puts me at 450. And here's where I got to, and I said, there, I'm done. But then if you try it on your calculator, 1350 divided by 450 just puts me at 3. But honestly, if you ended here, that's fine by me. It might be harder to work with later on, but this is an exact answer as well. Right? So you don't have to go to 3, especially if you don't have your calculator. Right? It'd be hard. Good. Okay. So let's see here. What's next on the docket? Let's talk about sets. So we already talked about sets briefly, but let's talk more about sets and how they behave and what we can do with them. So I'm going to go from here, maybe here. So a set is the basics of math, right? So a set is just a collection of things, and like we already introduced, we have the set of real numbers, right? Any number that we can think of. We have the set of integers. So they're just classifications of different numbers, right? We have sets everywhere, right? I can talk about dog breeds, that's a set. I can talk about different types of trees. I can talk about the letters in the English alphabet, for example, right? These are all sets. And so we're very familiar with with sets, right? And so a set is just a collection of objects, and we call these objects elements, right? So all these elements in a set, and we usually use capital letters to denote a set. So we usually use capital letters to denote a set. So if elements are in a set, then we need to develop some notation just so we're not having to write like the blurb that follows here. If capital S is a set, then the notation A, and then it's a little, it's like a stylized epsilon. So it's a C with a bar in it made to look like an E. It just says that's shorthand for is an element in the set. We use this symbol as shorthand for is an element in the set or is in the set, right? Depending on how picky you want to be. So if we say something like A is in the set S, what we're reading here is A is an element in the set S. Talking about some of those sets that we already introduced at the beginning of the class, right? We talked about the set of real numbers, we talked about the set of integers, natural numbers. So we know something like, stealing from the handout, -3 is in the set of integers, right? And pi is an irrational number, so it's not an integer, right? Integers are whole numbers, negative or positive, right? And so pi is definitely not an integer. So what we do is we just throw a line through it, is not in the set of integers. So here it came into play pretty quickly that we have to have a good handle on what integers are, what the set of integers are. Okay. So there's a couple of ways that we can give sets, right? So sometimes we might be able to list sets. We might be able to describe sets, or we might be able to describe sets using set builder notation, which is just a little bit fancier, but it's essentially a description. Okay, so if a set is small enough, we can list all the elements in curly brackets. Right? So if we have the set A is the set of numbers, so natural numbers less than 7, let's say, right? We can describe it like that, or we can say, okay, what I mean is 1, 2, 3, 4, 5, and 6. Another way that we could write this is to incorporate intervals if we don't just mean the counting numbers, right? If we don't mean just the integers, if we want to incorporate all the numbers between 1 and 7, not including 7, then what we can do is we can use set builder notation. So if a set encompasses a range, of values, we can use interval notation. Right. Along with set builder notation. So I should throw that on there too. Along with set builder notation. So set theory is a huge field, and you can get so deep in this kind of stuff, but set builder notation might look something like this. So we still have a capital letter for the set. We still start with curly brackets, but now to indicate that we want any x, we write any, so a lowercase x, and I'll just fill in here, any x. And then what makes it set builder notation is this vertical line, which we read as such that. So any x such that, and then we would have our description in what follows, such that, and we can say x is between 0 and 7, right? Not inclusive, maybe, right? That would be the whole range of numbers. All numbers between 0 and 7, not inclusive. Right, because I don't have the less than or equal to in there, I just have the less than. Okay. Which would be different from, so if I had to write this set, right, in set builder notation, then I could write A is the set of any x such that x is an integer and x is between 0 and 7. So that's set builder notation, and we'll read more about it, but it'll just kind of come up and we'll get used to it eventually. So usually we have more than one set, right? And so what we're going to talk about is the union between two sets and the intersection of two sets. So the union of two sets, now let me just see here. I gotta go grab it. It's okay. grab it from here, throw it in here. So the union of two sets, so if S and T are sets, you could use A and B, X and Y, these are just common couples. So if S and T are sets, then their union S union T, but the U, you can read as union, but it's more helpful to read it as or. Is the set that consists of all elements that are in S or T or in both, right? And so as long as the element is in S or it's in T or it can be both, then it's in the union of S and T. The intersection are all the elements, but only in the intersection. So how we read the intersection, so the union, we call it a cup, and the intersection, we call it a cap. And we read it as and, right? Because it has to be in S and T. How I remember it is we've got this cap, and I just make it an A and read it as and then of course the cup is just or because it's not and. But that's just how I remember it, and maybe you find it useful, maybe you don't. But you do have to know that the intersection is are all the elements that are in S and T. Okay. So we often visualize sets using Venn diagrams. We often visualize sets using Venn diagrams. So a Venn diagram just kind of looks like this. Got this rectangle here, and I've got my set S and my set T. So if I'm talking about the union, then I would have S union T or S or T, which means that I can pick any value from S, any value from T, or even if they're in both, right? So S or T can be from any of these regions. Whereas the intersection, you probably already guessed, because it's exactly what it sounds like, are only the elements that are shared. So here in this case, right, that's S and T. And then just to come back to the empty set is a special set that has no elements. So the empty set has no elements, right? And so what we do, we draw a little zero with a line through it, a diagonal line through it. So what's important is that if you draw your zeros, or if you write your zeros with a line through them, and I say that because my mom does, so I know it happens, but and it is good to indicate that it's a zero. I'm thinking like Wi-Fi passwords mostly, but anyways, but it actually means the empty set, so which is different from zero. So versus zero. So here we've got the empty set versus zero. Zero is an element in the set of real numbers. An element in the set of real numbers. Or if we want to get fancy, right, we can incorporate some of the notation that we just talked about. 0 is in the set of real numbers, right? So 0 is a thing, right? It's not a set, and it's definitely not the empty set. Okay, so let's do a little example. If I let A be the set of numbers 1, 2, 3, 4, 5, 6, 7, let B be the set of 2, 4, 6, 8, and C be the set of 7, 8, 9, 10. Then I want you to find A union B, A intersection B, and then we'll get a little wild and crazy here, A and B and C. Yeah. Keeping in mind that the U is or and the upside down U is and, right? And that should help you pick out the elements of each of these sets. So for this first one, if I'm talking about A or B, as long as the element is in either one of these, it goes into the set. So this set is often bigger than one of them. So I've got 1 is in A, 2 is in both sets, so it's definitely in the set A union B. We only list it once though, and order doesn't matter in these sets. So, and then we've got 3 in A, 4 appears twice, 5, 6 appears twice, 7 and 8 pulled from A and B respectively. Okay. So that's the set of A or B. If I look at A and B, it's going to be quite a bit smaller, right? So we said that 2 is in both of the sets, right? So it's in the intersection. 4 is in both A and B, and 6 is in both A and B. So we've got 2, 4, 6. Now, what I can do is A and B, I already know what A and B is. It's 2, 4, and 6. So now in C, I need to look for the intersection of 2, 4, 6, and 7, 8, 9, 10. Well, there's none, right? And so my answer here is just the empty set. Or I could also denote it just with these empty set brackets, but I actually prefer the 0 with the line through it. I think it's cleaner. But it's also cute to think of these curly brackets being empty. So we already talked a little bit about intervals, but let's go back and see if I should, yep, grab it, the little blurb. On intervals. So like I said, we've already talked about intervals briefly here, but let's talk about them a little bit more and just emphasize that intervals, you can either go to include the endpoints or you can exclude the endpoints, right? And so what we do is we can use brackets So round brackets is the same as just less than signs, right? So not less than or equal to. So that means not inclusive. Okay. So if I'm looking at a number line, right, any old number line, and I've got A here and I've got B here. If I want to show A, B both in round brackets, then what I do is I'm going to show open dot, and this line in between. Right? So the open dot or the not inclusive is just saying, hey, go as close as you can to A or B, depending on which one you're talking about, but not quite get there, right? So you can get infinitely close, but you'll never get to A or B, right? So that's not inclusive of A and B. Whereas if you include the brackets, so if you close the brackets, so square brackets, then it is inclusive. Right, so then it does include the endpoints. And you can do combos. Right. A, B, and what I'm showing is the square brackets, A and B. So now I've got these closed points and I'm including A and B. Right. I could even do something like, what if I did, here's A and here's B. What if I did something like closed on A, open on B, and the interval between? Well, that's going to be closed on A, round on B. So square on A and round on B, right? So you can do combinations. Yeah. It's kind of a three-pronged thing, just showing the same thing. But we can use the inequalities to indicate whether it's inclusive or not inclusive, right? So just the less than signs is not inclusive. Less than or equal to would be inclusive, right? So let's just talk about inequalities. First one is this little guy, which is less than. Okay. And I used to have a heck of a time because I would, like, the people always say the alligator eats the big one. That didn't really make sense to me because am I the alligator? Anyways, so, but then someone showed me if you just make an L, it won't work in the screen, but if you make an L with your left hand, right? So if you look at it and it actually makes an L, and then you put it down on your page here, and then you can read it as, so the less than, you can read it as an L. So A less than B, you would read it as A less or is less than B. Right, so just makes it easier because then if it's going the other way, then you know it's greater than. Right. If you've got a line underneath, then it's inclusive. Right, so here I would say not inclusive. Here we've got less than or equal to. The or equal to, of course, is the inclusive. It makes a big difference. And then of course we've got greater than and greater than or equal to. Same thing. Not inclusive. And inclusive. Good. So just 3 different ways that we can essentially just show the same thing, right? And we're trying to communicate numbers in an interval, right? And so we're talking about intervals here, which are essentially line segments. So we need to have a good handle on that. But for today, just so I'm matchy with the other course that's doing the same thing so I don't confuse myself completely, I think we'll stop here. Are there any questions? No? Okay. Then I'm going to stop the recording. Oh, new assignments. So I haven't posted any, but I will post some today, and then you'll have it today or tomorrow because I want to go through them. But from the time that I post them, you'll have a week to do them. Oh, thanks. I am using Notability. So Bon asked math, unrelated, but what are you using for writing and typing? Looks super seamless. Oh, thanks. Oh, it's an iPad. This old thing. But yeah, it's really fun. And it's, so far it's been good. But yeah, so I'll make a note on Moodle just in the little section about the new assignments, but I'll probably make them due next Thursday, so we'll talk about them on Thursday. So don't worry, you'll have lots of time to think about the assignments. Cool, awesome. Any questions, math or otherwise, are welcome. All right. Nothing to do. You can work on the WebAssign, getting started with WebAssign assignment that's posted. And then, oh yeah, so I'll post these notes right after class. They'll just be on Moodle. And then what I would recommend that you do is start reading the textbook a little bit, right? Make our way through chapter 1. And in case you're not sure, oh, and I did get them to, so I emailed WebAssign, I couldn't change it myself, but I did get them to extend the free trial till the 24th. So that's good. It was only a couple of days, but I mean, I don't know. So yeah, so here I'll post the notes that we wrote today. WebAssign. Okay. So for you guys, I've only got the one assignment up so far. I'll open the student view. So you should be able to make if you haven't already, you should be able to make a WebAssign account, and then we get 14 days of free access. So if you're not sure if you're staying in the course, then that's a good place to start, right? So I got them to extend it. It should be extended till the 24th. Let me know if it's not. And so you've got just the one assignment, just getting started with WebAssign. And then we went through these last day, but and we'll come back to them as we come closer to a test maybe, but it's got all these cool things like the class insights. It'll look at your assignments and see kind of which ones you struggled on, and then it'll say, hey, maybe you should study this section a little bit more, and that kind of stuff. And then I'm on an iPad, so it's at the bottom. I know if I'm on my desktop, then it's in the bottom right-hand corner, but either way, they've kind of hid the textbook, but you do get the ebook along with the WebAssign. So even with the free trial, you should get the ebook. Okay. So from here, we're just making our way through most of chapter 1. So fundamentals, that's where we started today. And we really only got through 1.1, not even completely, but it is the most important one, so, or one of the more important ones. But yeah, so you've got the textbook essentially to read through. So no assignments yet, except the getting started. Thanks, Finley. All right, if there are no questions, thanks, Fawn. Then I'll see you guys on Thursday. All right. Thanks, guys. See ya. Thanks, Jill.